Last time we can finish the random block construction. This is a probabilistic construction, but building on some existing highly structured graphs from geometry. And by mixing these two, it brings powers from both sides and oftentimes achieve much better bounds than just purely using geometric construction or probabilistic construction. And we've seen its application in Ramsey and application in a generalization of the Ramsey problem, so-called Erdős-Roger. So today we're going to move on to a new type of geometric construction. So most of the third part, the topic course on constructions, will be various different constructions using geometry. So the third one, which essentially made use of high-dimensional grid. And as we should see, high-dimensional grid is a little bit counterintuitive than a normal grid. So the first example is a very classical example on three-term arithmetic progression-free sets, subset of integers. So let's begin today's class. Lecture. This is 18. Okay. So let's begin by defining what is a 3AP free set, just to be on the same page. Definition. Definition. A subset of integers is, let's call it 3AP free if it does not contain any three-term arithmetic progression. That is a set of the form x plus k, x plus 2k for some k non-zero. Okay, this is we've learned this from middle school. How large can a set be without a subset of first n integers? So what's the maximum size? Wait, let me define the parameter. Maximum size of, let's call it Fn. Maximum size of 3AP free subsets of the first n integers. So let's first look at upper bounds. Upper bounds, first of all, Roth using Fourier theorem, Fourier methods prove a bound of it's little on sublinear. And later, Familiarity gave another proof using, this is Fourier, gave another proof, same bound, using the Rouge-Samarity, actually, sorry. Rouge-Samarity gave another proof using triangle removal lemma. Okay. Then later, many people like Gowers, Sander, um, um, many people like O'Gain also, they basically uh, use a more delicate, more advanced Fourier analysis methods to improve this bound to n over polylog n. Okay, n over polylog n. There's a long history, and recently there's a breakthrough by Mecca and oh, nice. I suddenly forgot the second author. Give me a second. There's a breakthrough by um uh, two. Where is it? And Kelly, maybe. I think. Yes, Kelly Mecca. There's a breakthrough. Basically, they prove an upper bound of the form n over e to the log n to some power. I think 1 over, let me put 1 over 20 to be safe, but please check some bound of this shape. So why is this a breakthrough? Because this is basically the right shape for the extremal function for 3AP3 sets. There is a well-known construction. This is what we will go through today by Beheron, so lower bound construction, which is known for a long time by Beheron. Proving that f of n is at least n over e to the, let me write it more precisely, 2 to the c plus little o1 square root log base 2n. So if you look at the shape, this is like e to the some constant times some polylog n. So where the power is strictly less than 1. So this is the correct shape. So before that, all the results, I think the best is like n over log n to the 1 plus epsilon. This is so this is a very, very important work. So let's look at how this lower bound works, where here c equals to 2 square root 2. Right. I will only sketch a proof of Beheron's construction. And so how it works is, let's consider let's consider a number n of the form q to the d, let's say. Q is a prime. We will determine Q and D later, optimize it later. The point is that we can now view let's view we can now we can write this first n integer in terms of its quinary expansion. So how do we do it? Each number, we're going to view it as, so you have for every, actually, I think I go n minus 1. Now for every x in here, we can write x equals to sum over I goes from 0 to d minus 1 xi times q to the I. Okay, quinary expansion. There's a one-to-one correspondence. This is one-to-one correspondence. So now we can view the first integers as like a high-dimensional grid, because we can just look at this vector, right? So every x can map to this vector x 0, x1, xd minus 1. The length d vector, this is the length d vector, which lives in, actually you can, for every x in this union, the element 0, okay? The all 0 vector correspond to number 0, so this lives in these sets 0, 1, to q minus 1 to d. We can have a one-to-one correspondence from a number to this vector. Let's define a map. Let's define this map, pi. So pi of x is this. Equals to this, all right? Okay, so what's Baron's idea? The idea, it's a geometric idea that, very simple idea. Every line can intersect any sphere at most 2 points. Any line intersect any sphere at most 2 points. Okay, very simple idea. I just draw the two-dimensional one, but it works for all dimension. How do we make use of this idea? Let's consider this high-dimensional cube, where the grid point of this high-dimensional cube naturally corresponds to the first n integers shifted by 1 through this quinary expansion. Now, let's draw this picture. So this is the high-dimensional cube. I can only draw 3 dimensions. Okay. Now what we do is, let's look at, this is the origin, 0, right? And this point is like q minus 1, q minus 1, q minus 1. This is the top right point. Right? Top right point. Now, let's draw sphere centered at the origin. Let's draw different spheres centered. Let's see what color I want to use. Let's say blue. Something lighter. Okay. Let's draw a sphere centered at the origin. So like this one, this one. This is sphere centered at the origin. Okay. Let's call it AR. So AR is all these points inside this q to the d minus 1, which is n minus 1, such that n minus 1, right? Let me just write n minus, okay, this is clear maybe. Such that pi of x, this corresponding vector, it has the same norm, same length, which is r. So look at the L2 norm, the little L2 norm, square equals to r. Okay, this is nothing but sum of xi square. That's it. I from 1 to d. 0 to d minus 1 maybe. Did I use 0 to d minus 1? Okay, sure. All right. Also, we're going to make sure that every coordinates of these points on the sphere that we take is in the first half. It does not go beyond q over 2. Okay, strictly less than q over 2 for every I. By pigeonhole, we then know that there must exist a sphere. This is our heavy one. So now the idea is, so how do we draw this sphere? Whenever there's a grid point, we're going to draw a sphere around it. Whenever there's a grid point, we draw a sphere. So the number of this radius is bound, you can bound it. And we have many, many grid points, which we also know how many there are, n grid points. And number of choice of this radius, we also know. By pigeonhole, there must exist a sphere that goes through many, many grid points. Okay, many, many grid points out here. Such that this is a heavy sphere, and we only take those on this sphere, we only take those where every coordinate is in the first half. If you want to see in the picture, this is the heavy sphere, right? We only take those where it sort of lives inside this smaller box, sort of first half of the box. Now I will leave it as exercise for you to fill in the details to show that because of this, it guarantees 3 AP free. So these guarantee 3 AP free. And then you can do the optimization. Wait a second. No, the first one guaranteed 3 AP free. This guarantee 3 AP free. Okay, this is because if there is a 3 AP corresponds to 3-term arithmetic progression in the grid from a line. Okay, so if there is a 3 AP, that means there are 3 points on this line lying on the sphere, which is contradiction to this geometric fact that every sphere intersects every line at most 2 points. All right. This implies AR can contain at most 2 points from any 3 AP, meaning 3 AP free. Okay. This second one is just to make sure that we don't have rounding issue. If you don't have index quinary expansion, you want to make sure that the lower digits does not add up, overflow to the next digits. Okay. This is to make each digit independent, sort of. no overflow. Good. Now do the optimization and check that everything will work. This is Behrens construction, giving a bound of the form this. So the construction today I want to talk about is how do we get a corner-free subset, a large one in 2 dimensions. So let's first recall what's a corner-free subset definition. As a corner, as the name suggests, I will draw some picture, is as a corner in Z2 are just basically 3 planar points that looks like a corner. 3 points, x, comma, y, x plus k, comma, y, x, y plus k, where k is not 0, or some k not equal to 0. It looks like this. You have the grid point. Now a corner is basically something like this. Okay, x, y, x plus k, y, where here k equal to 3. Here is x, y plus k. Okay, this is a corner. Like a corner. Good. How large? We can ask the same thing. A subset of n by n grid, if it's corner free, how large can it be? So let's let g of n be the maximum size of a corner free subset of the n by n grid. Now, the upper bound, once again, let's start with the upper bound. It's known that this upper bound is subquadratic. So whenever you have a positive density of points in n by n grid, you for sure will get a corner when n is sufficiently large. Upper bound is that Gn is little o of n squared. So maybe let's sketch this proof. I only sketch it. It's not the main part of today's lecture. Basically, you use triangle removal lemma. So basically, what we need to prove is need to show for any A, which is corner free, then for every A which is corner free, then A has subquadratic size. Okay, this is what we need to do. Let's construct the auxiliary tripartite graph. So we have A. Let me draw this A. You have A somewhere. I need to make sure I don't draw. So this is our A. Or for simplicity, let me assume not that k is bigger than 0, not 0, just assume k is strictly bigger than 0. So the corner goes like this. This type of corner, it's the same. If you forbid both, It's the same. Let's just, for simplicity, consider this direction. All right. Good. How do we construct? We construct the auxiliary tripartite graph. Tripartite graph on vertex sets x, y, z. So what's x, y, and z? So x, y, and z, right? 3 parts. Where the vertices in x are all the horizontal lines. In the grid. Every one of this line in n by n grid, this is in n by n, right? You make it a vertex in x. Every vertical line in this grid, you make it a vertex in y. So here y is vertical lines. So here's y. Now every lines of slope -1, slope -1 lines going through some grid points in n by n, we make it a vertex in z. So this is z. Z is like here. Oops. Right? You get the idea. I will not draw all of them, till the last one. So what's the size? Well, this has size, if you want to be precise, let me write down what is x. X is y equals to I, where I in n. It has n horizontal line. This is x equals to I, where I in n. So n lines. Here there are 2n slopes of -1, which is x plus y equal to I in 2n. Okay. How do we make adjacency? Two lines, corresponding lines, you add an edge. If their intersection point is a point in, so x adjacent to y, if and only if you look at their intersection point, it lies in A. Okay, for example, this is my x, and this is my y, and here is the intersection point. Okay, their intersection point lies in A, so you put an edge there. All right, good. First of all, how many edges in this graph G? This is my auxiliary graph G. Okay, how many edges? Well, notice that every grid point in A, generate triangle, because these two form an edge, these two form an edge, these two form an edge, right? These 3 lines, which correspond to 3 vertices in x, y, z, they all intersect at the point in A, common point. So they form a triangle. So note, each point in A generates a triangle in G. And all the edges are generating this way. So that means, and also these triangles are edge disjoint. And these triangles are edge disjoint. This is also easy, right? This generates a triangle, this generates triangle. For two different points, the triangle Y is edge disjoint. If you have two triangles sharing an edge, that means the corresponding three lines, there are two lines identical. If two lines are identical, this point is already fixed. So they cannot correspond to two different points in A. Okay? These triangles are edge disjoint. And this generates all edges of G. So that means the number of edges in G equals to 3 times size of A. So we get, E of G equals to 3 times A. Now let's try to prove the contrapositive. Suppose A is, suppose to the contrary that A is quadratic size, has positive density, then we will get G contains 3A, which becomes quadratic, okay? Contains A many, which is quadratic many edge disjoint triangle. This, using the contrapositive for triangle removal lemma. What does triangle removal lemma say? If a graph has quadratically many edge disjoint triangle, then this graph must have cubic number of triangles in total, a positive triangle density. That means G contains, in total, cubic number of triangles, which is much more than size of A. A has size at most n squared. Here, when n sufficiently large, of course, this is larger. That means G contains a triangle that is not a triangle generated by a point in A, not a triangle that looks like this. Okay? This implies there exists a triangle in G not coming from a point in A. Well, how can a triangle look like in G if it does not correspond to such a point in A? Well, we claim that it must look like this grid. Okay? Such triangle corresponds to a corner. Sorry, not grid, corner. Okay, why is that true? Right, x, y, x plus k, y, x, y plus k. They are all in A. It corresponds to this because then, if you look at the three, what color do I use? Vertical is blue. So if you look at these three vertex, which correspond to the three color lines, right? This line in G. I will not draw. So in G, this is adjacent to this because this point is in A. This adjacent to this because this point in A. This, this point in A. So the only triangle that's not corresponding to a single point in A has to look like this if you think a little bit. That will conclude the proof. We get that A is not corner-free, contrapositive. Contradiction. Good. That's upper bound, lower bound for corner-free sets. one can actually make use of Behrens construction to get a lower bound. Use Behrens construction. We can get Gn is at least n squared over 2 to the c plus little o1 square root log base 2n, where c is 2 square root 2, about 2.828. How do we make use of Behrens construction? This is easy. So what do we do? Let's start with, here's how we do it. Well, I wouldn't say it's easy, it's smart. The construction is short. We start with a 3 AP free set guaranteed by Behrens construction, which is large. So let B be a subset of first integer, which is 3 AP free. And the size of B equals to this, n over 2 to the c plus little o1 square root log 2n. Okay. Now what we do is we will get A, let A B as follows. We define A such that we're gonna take x, y in A if x minus y is in this 3 AP free set B. What does it mean geometrically? Let me draw a picture. Here's an n by n grid. Okay. On this line, this is the one-dimensional grid where we have this our set B. Oops. We have our set B, right? This set B is 3 AP free. This is B, 3 AP free. Now, let's draw this a line. Oops. Okay, draw this line of slope 1. This is basically A is the form. A consists of, remember, for every point in B, it generates one of these purple line. I didn't draw all of them, okay? I didn't draw all of them. So this is actually a line here. So A consists of parallel lines. Slope 1 lines. And you're going to take all the, so the A is what? You take all the points. You take all the points on the line, grid points. You put it in A. You put this in A. Now, if A has a corner, we claim that A is corner free. Basically, it's easy. If there's a corner in A, it will correspond to a 3AP in B, which is a contradiction. We know B must be 3AP free. Why? Let's draw a picture. If you have a corner, it looks something like maybe like this. Okay, this is a corner. If you have a corner, maybe look like this. If you have a corner, you take these 3 points in a corner. Now you project it along this -1, slope 1 line down. You look at the corresponding points in B. They must form a 3AP. Okay? This is easy because this is xy, right? This is x plus ky. This is xy plus k. So what is this point? This point is x minus y. So it's x plus k minus y, right? This is x plus k minus y. This is x minus y. This is x minus y minus k. So the common difference is k. 3 points. Done. This is the construction. This was recently improved by linear entrapment slightly. And the construction we're going to present is a further improvement building on the idea of linear entrapment by Green. So improvement. This linear entrapment, and we're going to see Green's construction. We will achieve G of n is at least the same form where the constant C is improved. Okay. So this is what we're going to see, where C is 2 square root 2 log base 4/3, which is roughly 1.822. We improve from 2.8 to 1.2. 1.8. How do we prove this? I would say it's sort of like a two-dimensional version of Beheren's construction. So again, let's consider n. Where is it? Let's consider n of this form, q to some power d, and we can now associate n by n grid, every point here, to a vector y xy of length 2d now. Before it's length d, right? Now we can do the same. Consider quinary expansion. So now, before in Beheren's construction, let's recall, what do we take? We take set AR on the same sphere, and every coordinate must lie in the first half. Now we take again quinary expansion, associate a point x, xy in n-1 square right? You get associate to pi x pi y, where again, this is the quinary expansion. Okay, we're gonna consider sets AR now, construction. We can consider set AR of the following form. Where AR consists of points x, y, such that it satisfies two things. Containing points x, y, such that the distance between x, y in the high dimensional cube, so every point in the grid, in the planar grid, correspond to, we map to this pi, right? To high dimensional grid. If their distance is a fixed number r, this is the r here. And we also require, this is the first requirement, each coordinate, we have a similar requirement. In the reference construction, we require each coordinate xi live in the first half, 0 to q over 2. Now we require xi plus yi lives in q over 2 and 3q over 2. Okay, for every I from 0, 1 to d minus 1. This is the construction. Well, let's first prove that this set AR is indeed corner-free, right? And then we're going to do optimization. Claim this set AR is corner-free. It does not have 3 points forming a corner. Why is it true? Suppose we have a corner. Proof. Suppose there exists a corner xy, x plus ky, xy plus k in AR. We have some corner. Well, these 3 points being in AR, what does it mean? That means their corresponding hypergrid points, they pairwise at a fixed distance r. So by 1 implies that the length, the distance between these two coordinates of the grid points between x and y, between x plus k and y, and between x and y plus k are both r, are all r. They are all r. Okay, no problem. Let's prove a subclaim. Let's call this we claim that the subclaim is this called inequality identity 2, equation 2, that x plus d, the grid point, and y, the grid point, their sum is the same as the vector x plus the vector y plus d. This is natural. If you forget about vector form, just look at number. X plus d plus y is the same as x plus y plus d, right? This is just saying that if two number, their sum is the same. If you distribute some part to the other term, look at the vector form, they are still the same. The vector sum is still the same. We're going to prove this by induction over coordinates 0 to d minus 1. So let's prove it later by induction. Let's prove it later, assuming this equality 2. Let's prove that this corner would derive a contradiction. So assuming 2, now let's define A to be the vector, which is the difference of pi of the vector x and y, and define B to be the vector, which is the difference between x plus k. I wrote something wrong here. This should all be k. Minus pi of y, no, pi of x, the vector x, which equals, by the second inequality we prove above, this minus this is this minus this guy, so equals to pi of y plus k minus pi of y. No problem. Okay, now what 1 implies what? The norm of, so here we get the norm of A square is R, right? Equals to R. And what is A plus B? A plus B is this minus this. X plus K minus Y, the vector. So A plus B has also norm R. What about A minus B? I claim that it's the same. A minus B means, let's look at this form. This minus this, these two get canceled out. You get pi x minus pi y plus k. So all three vector has the same norm R. But these are not three random vectors. These are three vectors in the parallelogram. So let's draw this picture. You have these three vector. This is A. Well, this is pi of A. Oh, no. We already define A as the grid, hypergrid point. This is B, okay? And this is A plus B. What is A minus B? A minus B is this guy. A minus B. Maybe let me use a different color. This is A minus B. Okay, so this drawing is really bad. Well, You know what I mean? Um, so you have A and B, A minus B and A plus B. Parallelogram law, how do you spell? Parallelogram law says what? It says that in the parallelogram, we have A plus B norm square plus A minus B norm square equals to 2A to 2 diagonal norm sum up equals to 2 times the 2 sides square. Now, what is the left-hand side? This side is 2R because of this. Okay? This is already 2R. This is also 2R. That implies B must be 0. Okay? There's no norm left for B. So this implies B equals 0. What is B again? B is this guy. This implies if B is 0, and remember, that implies K must be 0. These two, B 0 means these two are the same, right? i.e. pi x plus K equals to pi of x. But this pi, the projection, this pi associating grid points to high-dimensional grid is one-to-one correspondence, is injective in particular. As pi is injective, this implies x equals to k, right? In particular, k equal to 0. What does it mean k equal to 0? We'll get a contradiction. Well, we assume we have some non-trivial corner, right? K bigger than 0. This finishes the proof that AR is corner free, assuming this. So that's proof 2. How do we prove this? Left to show this. This is, as I said, induction, and that's where we use this part. So this part implies corner free. This is also sort of for proving 2, but it's also make sure that there's no overflow issue. So the digit is also to maintain digits being independent. Same thing as invariance construction. What do I mean? Let's see. Basically, we want each coordinate. There are d coordinates. Each coordinate just do what they do. There's no interference between coordinates. Here's interference means, no interference means these two are the same. That means every coordinate are the same. Let me write it down. This is what you mean by induction. Induction on I equals to 0, 1, b minus 1. So let's assume true for any I less than j for some for some j bigger than 0. Okay, so suppose it's true. This is we're going to do directly the induction hypothesis, induction step. Now let's write this x bigger than j. What does it mean? This is basically, you have this vector form, right? x1, xj plus 1, xd minus 1. This x bigger than j basically is saying, let's just look at this part. Forget about the previous digits. So x bigger than j equals to the sum of I at least j xi times q to the I. This is what it is, something like this, right? Now, induction hypothesis implies what? I forgot to tell you what is the induction. Sorry. Induction on this to show that x plus k, this is a vector. If you look at its ith coordinate plus y, this vector is ith coordinate equals to ith coordinate of x plus y plus k ith coordinates. You want to prove these two vectors are the same, right? Let's just prove by coordinates that they are the same. And now assume it's true up to coordinates before j, for some j greater than or equal to 0. Let's write the later digits like this. Induction hypothesis says all the previous digits are the same on both sides. And we also have as the sum, the total sum is this number when you sum it up in terms of quinary expansion. So that implies that this is the same. Let me write it down. Induction hypothesis plus x plus d just as a number, the grid point equals to, k. It's k x plus y plus k. This is trivial in 2 dimensions. Because of this, plus all the previous digits being the same, so all the later digits also should satisfy this. We get x plus k greater equal than j plus y greater equal than j equals to x greater equal than j plus y plus k greater equal than j. Okay. Now, this then implies this sum, this thing be the same. If you modular q, that means their smallest digits must be the same, modular q. Okay. Yes. So this implies their smallest digits, x plus k j plus yj equals to xj plus y plus k j mod q. All right. So here is where we use this this requirement on the choice of x, y points to maintain no overflowing issue from lower digits to higher digits. So by by this inequality. Let me just recall it. Okay. Recall each xi plus yi, if xy is in AR, we have this is between q over 2, 3q over 2, right? In particular, this means this equality actually holds without mod q, because this is also a point in A, right? This is also a point in AR. So these both should satisfy this inequality. The largest it can be, mod q cannot catch up, cannot wrap over to the smallest element. So this implies equality holds without the modular q. Okay, good. So this implies both sides above in q over 2, 3q over 2. Okay. That's it. That finishes 2. Induction. Any question? Looks a little bit lots of actually not many calculation, but let me draw some picture to compare this proof with Behrend's proof. Let me finish by telling you the choice of parameters. What is the size of AR? Size of AR, to compute it, let me start a new page maybe. So size of AR, just let's do pigeonhole. Well, there are n points total in the grid n by n. And the number of choices for R, remember what is R? R is the length, the distance between x and y, taking a square. And both x and y are length d vector where each coordinate is basically 0 to q minus 1. Okay? X and y, these two are basically in here. Or to be precise, 0 to q minus 1 to power d, right? So their distance at most is difference is q. So q squared times d. This is the number of choices for R. So number of choices of R is at most d times q squared. Now remember, when x, y is a chosen point in AR, it satisfies this inequality. That for every I, xi plus yi is between q over 2 and 3q over 2, right? The number, this size is roughly 3 over 4 q squared plus some lower order term raised to power d, the number of choices. This is the number of points satisfying this. Why? Let's draw some picture. For each I, we have d coordinates, right? For each coordinate, xi, yi, so if this is xi, this is yi, they must live in this strip that their sum is between 2q/2 and 3q/2. So something like here. So they live in here. This is where they live in, right? And the area, this number of grid points here is roughly 3/4 proportion. Good. This implies that AR is at least, well, the total number of points satisfying this condition in all direction D is roughly this much, divided by the number of choices for R, so which is D times Q squared. So the optimal choice, we're going to take Q to be actually a function of D, this choice. All right. This is how we pick Q and D. How do we compare this construction to Behrens' construction? In Behrens' construction, actually, if you recall, Behrens there, we actually require, instead of heart, we take all points pi x. Okay, let me write it. All points pi x, where the norm is. Let me not write this irrelevant part. Let me just write the relevant part that we require, we only consider points xi, where its norm is between 0 and q/2. So it's sort of like here, 0 to q. You only take this part. In the two-dimension, you can pair up coordinates in Behrens construction. Think of it as a two-dimensional version, as what we did here, xy, right? Xy. Then it will look sort of, some sort of way of comparing these two. If you paired it up, this is xy, yi. This condition is basically the same as saying we only take points where xi plus yi is between q and 0. Then still, mod q, if two things are the same, mod q, then two things are the same without mod q. This is basically what we use for heart, right? How we use for heart to overcome overflowing issue is that if the sum of the coordinates are the same mod q, then they are the same without mod q. So the corresponding area is here. And simply look, this area is roughly q²/2, right? Here is 3q²/4. This is larger. This is one way of comparing these two. Okay. Any question? So this is how to make use of high-dimensional grids. Now let's introduce another problem where high-dimensional grid provides a really good construction, which disprove a question of answers a question of Erdős and Rothschild in negative. This is a question about how large a book can we guarantee in the a graph with positive edge density, and every edge appears in a triangle. Okay, so let's not talk about corner-free sets. Let's go back to graphs. Any question for this construction? Okay, if there's no question, let's move on to the next problem. This is Erdős Rothschild problem on edges in many triangles. To some books, maybe. What is this problem? Let's introduce some background. A book is nothing but a bunch of triangles sharing one common edge. Recall, a book is, let me not write down the definition, let me just say, this is a book. A bunch of triangles sharing one common edge. This is the common edge. This is a book. The book size is the number of triangles. So the book size is the number of triangles in here. Easy. Mantel's theorem says what? If we don't have triangle or no book, you have at most n squared over 4. So, okay, wait. So by Mantel's theorem, we know, take the contrapositive, we know that for any m vertex graph, if E of G is at least n squared over 4 plus 1, then there will be a triangle. It's a book of size 1, basically. Is this triangle, which is book size 1. Okay. It turns out we can actually get a linear size book. This is proved earlier, I believe, by Erdős. And then he conjectured that you can find a linear size book. You can even prove n over 6, the constant n over 6 book. You have n over 6 triangles sharing one common edge in any graph with one more edge above the Mantel's bound. This was confirmed independently, so this turns out to be true by Edward, and independently Kazhivanov Nikiforov, that under the same condition, actually there exists a n over 6 size book. Now, the problem with having needed, the problem of how do you phrase this sentence? we need this many edges simply because complete bipartite graph has n squared over 4 edges. And many of these edges, none of these edges lies in a triangle. So this prompted Erdős and Rothschild to ask the following question. Can we lower this edge density threshold? So to, let's say, as long as you have positive edge density, you have epsilon n square edges. If we know it's not like bipartite graph, if we know every edge appears in at least one triangle, then can we guarantee a large book, a book of size polynomial in N? That's their question. Let's rigorously formulate this. Problem is, what if every edge must be in a triangle? Does it change the, can we lower the edge density and still guarantee a large book? Can we get a large polynomial size book at lower edge density? So formally, let's define this book function, let's say Bn row. So maybe let's first define B of G is the size of largest book in G. The maximum number of triangles sharing one common edge. Now we define this to be the largest book size in any m vertex graph G with row n choose 2 edges, where every edge appears in at least one triangle. Is in at least one triangle. Okay. In other words, this is mean over BG, where G is m vertex. E of G is row and choose 2. Every edge in G in the triangle. This is the Bn row. Now the conjecture, Erdős and Rothschild conjecture that for any positive edge density, meaning for every positive constant row, when n is sufficiently large, this is polynomial in N. We can always guarantee, as long as every edge is in the triangle, a polynomial in N size book. Question. Erdős and Rothschild. For every row bigger than 0, Bn row is at least n to the some constant, depending on row, only depending on row. Okay. Seems not completely impossible. And it turns out, well, first of all, by removal lemma, a remark, by removal lemma, one can indeed find a large book if every edge is in at least one triangle. This will imply a lower bound of the form, but much smaller, e to the some constant times log star n, which this is an iterative log function of n. Whatever, you can obtain some bound. This was disproved by Fox and Law about 10 years ago. That's the construction I want to talk about next. So, theorem disproved. This is theorem by Fox and Law in 2012. That they found the graph G m vertex, of course, with edge density close to 1/2, 1 minus e to the negative log n to the 1/6. So 1 minus little o 1, n squared over 4 edges, and every edge in the triangle. But the book size is not polynomial in n. It's at most subpolynomial. It looks like n to the some constant over log n. Okay. This is their results. Now I have 3 minutes. Let me first tell you a high-level idea of their construction. And then we're gonna lay out the details next time, right? Next week. So idea, what do we need to do? We need to, well, first of all, remark this edge density 1/2 is obviously optimal. Edge density of G 1/2 is optimal because of these Edwards results, right? If you are going above n squared over 4 plus 1 edges, even without this condition, you get the book of size n/6. So there is a sudden drop from linear in n book size. When you just have slightly fewer edges, you drop from linear to subpolynomial. Okay, dropping from linear to subpolynomial. So there's this transition of book size at density 1/2 from linear, well, n/6 actually, to subpolynomial here. Very quickly, okay, I would so the graph they constructed very quickly is you have sets A, B, and C, which is again high dimensional grid. Let's say R to the D, A, B, and C. Same sets, make 3 different copies. Now I made A and B. I add almost all edges between A and B. How do we add edges? For A, B, we make them adjacent if and only if the distance is a typical distance. And here is a not so intuitive property of high dimensional cube. In high dimensional cube, almost all pairs of points, their distance is at some typical distance mu. This is a key property that we will use. So you have almost all pairs, they are at typical distance apart from each other. You have almost all edges in between. How do you add these edges? These edges, well, much fewer edges, is that, so you have A and B at typical, their distance is usually typical distance, plus minus some error, right? Now, you add point C to A if C is roughly at the distance half of this typical distance from A. So C is roughly, so A is like this, B is like this. All these points, C will be adjacent to both A and B. Okay, that you will find. So AC and AB, similarly, if the distance is half. Half of typical distance, right? Okay, we will show next time that this geometric construction will give us what we want. Well, later you actually also have to blow up these two parts to boost up the edge density. All right, so that's what I want to talk about today. Next time we're gonna see the details of this. Any question? Okay, there's no question. I'll see you guys next week.